Good afternoon. So in this presentation, I want to go over a couple of things that you can do with Maple to visualize the volumes of revolution with Maple. So if you access Maple either on your own computer or at the lab, I strongly encourage you to actually play with some examples. In particular, if you have trouble visualizing the shell method, the slicing method, and how these volumes are computed with the Riemann integrals. There's a nice tool you can use, and I'm going to show you actually at the end of the presentation, because in the beginning I want to go over a couple of examples. So it's very easy. You don't have to actually memorize. I mean, you can copy the command that you see here that I wrote, but there's also an interactive menu in which you can change the functions, and you can play with some other examples. So again, it's very important to go over this type of examples with some computer algebra system if there are some troubles visualizing the regions, because like I said in the video lecture, by hand sketching, it has some limitations in problems like this. So you don't have to sketch much, but you need to sketch enough so you can figure out the domain of integration and things like that. So first thing first, the volume of revolution command belongs to the package student calculus 1, so make sure you pay attention to the syntax and enter the with command that you see here. And I'm going to show you first with a simple example the region below the function y equals x squared. So in this example, we're going to use functions with respect to x. In other words, the integration will be with respect to x only, though I think you can change that later if you want to. So this is the region, and as you can see here, I hope this is pretty obvious what this picture represents, right? So in the dark red, I think, I'm sometimes bad actually calling the colors by the correct name, but I hope you see here below the blue line, that's the region that is rotated about the x-axis. So the axis of rotation is horizontal. By default is the x-axis, or you can choose any other horizontal axis by specifying the distance to the distance from axis. So you see here this is 0. You can make it to be a different number. So for instance, if I have distance from axis, let's see if it takes a negative number. It should take a negative number. Yeah, there you go. So now the axis of rotation is below the x-axis, and the region, and basically the shape now is a hollow object, right? So I mean, there's a hollow part in the form of a cylinder. On the other hand, if like I said, if you leave the 0 here by default, the axis of rotation, let me see if I can make this a little bit bigger so you can see the command here. So if you leave it 0, then it's going to be the x-axis, and there's no hollow part, right? So if we look from the side, everything is filled in. So as long as if you see a color here, that means there's no hollow part. Okay, so we visualize the volume here. If we choose in this type of command, volume of revolution, if we by default, if the axis of rotation is horizontal, the method shown will be the disk method. So if you choose the parameter here, show sum, if you change it from false to true, what it shows is going to show you the slices basically that come up with the volume. And the partition number here is the number of slices you want to show. So this is basically the shape of each slice. I gotta say, sometimes it's kind of confusing because in reality each slice should be filled in, right? There's no empty spot, but because they use different colors so that the object is transparent, sometimes it looks like they have a hollow part in the middle. But again, each slice is essentially a disk, a cylinder. So 4 slices, one of them is basically 0 because it starts from 0. One of them is degenerate, so to speak. And what it's important to notice here is that, again, the integration is going to be over the interval parallel to the axis of rotation. So slicing method, that means integration is over the interval parallel to the axis of rotation. So in this case, it's just the x-axis. So I hope it's clear where the integration is with respect to x, because as you can see, you fill in the volume with these disks, with this yeah, I mean, you can call them disk if you fill it with these slices. Then basically you go over the x-axis until you fill in the volume. If you want to see more of them, so if I put, for example, 10 partitions here, now you see lots of slices, and they will approximate even better the volume. If I put 100 slices, I shouldn't see much of an error with the naked eye. So it should be pretty smooth. It might take actually some time. I hope I didn't get too greedy with, yeah, there you go. So now the slices are so thin that you can't see, or you barely see each of them. And now clearly the volume is computed correctly. I mean, it's close to the real, to the exact value of the volume, if you have a bigger partition. All right, so let's go back to 4 disks. Now, if we change the axis of rotation, so we keep the same function, y equals x squared, but now we have let's see, we have the vertical axis as the axis of rotation. So let's choose axis from horizontal to vertical. Here you will see the shell method. So actually, let's go back to the region. Let's see only the region first. So let me deactivate the Riemann sum for a moment. Okay, so now actually you have basically the region rotated is the one again below the function. So the object is basically a cylinder with a hollow part in the middle, right? If you look it from above, that's hollow, right? Because the dark region here, that's what's rotated about the y-axis, and so what's in between here, what's in the middle, it's an empty. In other words, above the graph, that's going to be the hollow part. Now, because the integration is with respect to x again, here you're going to see the shell method. So imagine how you scoop out thin cylinders from this object and you add them up to compute the volume. So now let's go back and see actually these shells. And I think this is a little bit better to visualize. Okay, so these are not slices, right? These are cylinders, thin cylinders that are scooped up. Again, integration is with respect to x, but now in the shell method, integration is over the interval perpendicular to the axis of rotation. So remember, shell method, you always integrate over the interval perpendicular to the axis of rotation. In this case, it's still the x-axis because here the rotation is about the y-axis. I'm saying this because, of course, you could change that. I mean, if you decide to use the shell method for a horizontal rotation, then it's going to be the y-axis, the y variable for the variable of integration. So it's basically the other way around. Let's actually show more partitions here so you see how this volume is computed. So let's do 10 partitions. Now you see more of these shells, but thinner and thinner until they will basically fill in the full volume, right? So let's do 50 of them. And might take a while. And now you clearly see the volume with the hollow part in the middle there. All right, so how can you do this on your own? Well, there is something called Tutors in Maple. So if you go to Tools, Tutors, and then you choose your class, calculus single variable, and here you have various tutors for various applications. So in our case, the volume of revolution, and here you can play with the function. So it's more interactive than what you see before. And then once you come up with the elements you have here, the functions and so on and so forth, you have the Maple command that gives you that figure here. So then you can copy the Maple command and then you can tinker with it so that you don't have to launch the tutor all the time for all examples that you want. So here you have a nice function, portions of the function 1 plus cosine of x. Let's actually use one example from our presentation. So I think we had one function x squared and the other function square root of x between 0 and 1. One example that we did display, and then you can click on the region, display, so you can see the region here rotated, hollow part. Then you can see the disks if you want. And then to be more efficient, like I said, you can just copy the command here, and then you can close the tutor. When you close the tutor, you have it usually gives you the picture in the worksheet. I don't know why it didn't show it, but anyway, you can enter now the command, and then you have the picture there bigger, and then you can manipulate it here. Then you can change the partitions or the functions if you want. Let's say I want 20 partitions this time around. See if I can see the volume better with the hollow part in the middle. So that's it for this presentation. I'll see you next time.